Alrighty, so from last class, we just did this massive warm-up all the way through. So let's just kind of go through. So we did a few different problems. For number one, we used bond enthalpy values, right? That's one way we can get to an enthalpy of reaction value. Or in this case, get to the enthalpy of formation. The trick here was recognizing that since we're solving for enthalpy of formation, that's a kilojoule per mole value, right? That's going to be per mole of water. So since our balanced equation is making 2 moles of water, when we get that final answer, we have to divide by 2. So that was kind of the trick there. Number 2, we looked at determining the enthalpy of reaction for the decomposition of hydrogen peroxide. So all we did was used our enthalpy of formation values, looked at what was being formed and what was being broken, right? The water is being formed, the oxygen is being formed, but that's not because it's 0. But the H2O2 is not being formed, it's being broken, so that's why we pop that extra negative sign out front. We are flipping the sign. Remember, it's not this one's positive, that one's negative. That's not what we're thinking. You use the numbers as they're given from the data tables, and you think about where the data is coming from. If it's enthalpy of formation values, those are from the forming of molecules. So if the molecule is not forming, i.e. if it's a reactant, that means it's breaking apart, so you need to give it that negative sign. We also then labeled, if it's a negative value for that delta H of reaction, then we know that that's an exothermic reaction. We then went ahead and drew our potential energy diagram, showing products lower on potential energy than the reactants, therefore energy must have been released. Seeing that we can identify the delta H, the activation energy, we could think about the reverse reaction. Next class we'll play with what if we have numbers on that potential energy diagram, can we use that to calculate our enthalpy of reaction? And we can, so we'll do that next. Number 3 here. So now we use this different enthalpy value, just enthalpy of combustion. Again, it's just for a specific kind of reaction, and this is for the combustion of methane. So when we have this kind of a value, right, it's for a specific thing. Again, it's a per mole value. So being able to recognize, are we looking at something that's specific to one of the compounds, then it's a per mole value, or is it just generic for the reaction? Then it's just an overall for one reaction kind of a value. So here we're burning our 10.5 grams. All we have to do is convert grams to moles. Then we can use that enthalpy of combustion value as a conversion factor to get us to our kilojoules. And 3b, same again, but this time I want to talk about producing water. So now you have to do some stoichiometry as well. You got to get that balanced equation, and we need to see how much methane are we burning if we're making 30 grams of water. So we get our balanced equation, and then we start with our 30 grams of water. Grams to moles gets us to water. Mole ratio from the balanced equation gets us to moles of methane. And then again, that enthalpy of combustion gets us to our kilojoule value. And again, we talked about double checking your answers, making sure they make sense, right? Both of these make sense. We had less than a mole of CH4, so we should have less than a mole's worth of heat being released. Here, we're producing less than 2 moles of water, so we should have less than 1 full moles of CH4 is released based on that balanced equation, okay? So there's those. Then moving forward, I threw this one up for you guys. So I wanted you to do this calculation, using enthalpy of formation values to get the enthalpy of reaction, and then use that enthalpy of reaction to figure out how much is what's a limiting reactant problem, actually. So this is more of a kind of combined problem. So here we're going to fill in our numbers. So I promised I'd work through this. So hopefully, here we go, except now my pencil is dead, so I can't. So I'm going to take it back, and I'm not going to work this out for you because my day is done and I want to go home. So, so all you would do here, the pencil's dead, so I'm not going to bother. But you would get your enthalpy of formation values from your data table, plug them in, right? Flip the sign for the reactants because they are breaking and not forming. All of this after you balance the equation, which it's balanced, and then add it all up. That gets you your enthalpy of reaction. So that would be the energy released for each reaction that happens, right? Then for part B, it's a limiting reactant problem, right? So is the 5 grams of sodium hydroxide or is the 5 grams of HCl your limiting reactant? So figure out which one's limiting. That'll tell you how much of that you're going to use or how many reactions you're going to go through. You can then go ahead and use that enthalpy of reaction as a conversion factor at the end to get the total amount of energy released or absorbed. We can start the class next time with this. Again, next class, we're doing wrap up and review, and we will pull it all together for the test next week. All right, happy studies, and I'll see you in the morning.